And this next presentation that Jim Kolbus from Clark-Reliance is going to talk to us about on drum level instrumentation was provided to the European Forum earlier on in this year in May. And Bob and I thought that it was excellent, so I wanted to share it with this group. So Jim, please go ahead, introduce yourself and go ahead with the presentation.
All right, thank you, Barry. My name is Jim Kolbus. I'm with Clark-Reliance. I'm a product manager here, just short of 40 years with Clark-Reliance. And we're just getting our screen ready here for just a second. Should be ready in one moment. There, are we good?
Now you are.
Yeah.
All right, very good. So in any event, this presentation you're about to see, and I wanted to have this opening slide up. We are going to be focused on the boiler drum area as well as the operating area in the controls area as well. We are focused today on discussing the direct and indirect remote reading level indicating devices. We're going to be discussing isolation and drain valves, piping concerns, some common code violations that we see, some of the supporting applications for boiler drums, including condensate tanks, feed water heaters, and such. Some maintenance suggestions for you. Also keeping in mind some of the other auxiliary boilers. Some of these applications can become neglected over time, and we see a lot of ways where we can help. We do this presentation for boiler inspectors, end users, contractors, OEMs. You see a cover of a booklet there in the lower right-hand corner of the screen. We offer two forms of this booklet. These are available at zero cost. This is a boiler inspection guideline for ASME applications. And also we have a abbreviated version for PED applications referring to the appropriate EN standards. So without further delay, let me go ahead and get started. And in the applications in water level for direct read gauge glass, there really are four technologies that are available in the marketplace. Tubular glass, which you may see on a feed water heater or some very low pressure application. 17 bar, 250 PSI is really the limit for those, but that is the thinnest glass in the industry. So in many applications, especially on steam and water, no matter the pressure, many users and operators try to upgrade to at least a reflex, also known as a prismatic type glass, which has a prism molded on the inner side of the glass that interfaces the steam and water, and the water line and below appear black in color, and the area above appears white or light gray. And those prisms, when their ambient light is in front of the gauge, reflect ambient light. That's why you're seeing a gray or white area up above. But when they're in contact with water, you're actually looking into the depth of the gauge. And with glass on the front and metal on the back, you're looking into the cavity of the gauge, which is what causes it to appear black. On the third type, transparent or flat glass gauges, as they are known, there's a glass on the front of each window section and a glass on the back side of each window section, and they're illuminated from behind. You might say it's like looking at a glass half full of water on your table. You're looking for the meniscus line or water level line. Under pressure, steam and water are both transparent in color. So if you lose sight of the line in this type of gauge, you lose the ability to read the level. This type of gauge, when illuminated properly, is illuminated from behind. And this is an overlap section shown of a two-section gauge. Hence, you see the two bright star images of the water level line in the overlapping sections. The last type of gauge is known as either ported or bicolor. And those types of gauges in industry standard, water is displayed as green, steam is displayed as red. And as you see with all these different types of gauges, these are the respective maximum design pressures used throughout the industry for the various types. Moving on, a bit more detail on the reflex gauges. ASME defines these as being permissible without overlap. If you look at that image in the center of the screen, you'll see that these two gauges in this particular case, maybe two window sections were required to cover the total amount of range that's required for the application. But you see there's a blind spot between the two sections where one stops and one starts. However, as I mentioned earlier, with water line and below appearing black, if that water line were right in that blind spot, the bottom section would be black, the upper section would be white. It would be very obvious to the operator where the water level is being at that moment. If it were a transparent type gauge and you lost the level in a blind spot, you would not know if the gauge is full, middle, or empty, which we'll get to in an upcoming slide. So here off to the right, you can see those prisms that are molded on the inner side of the glass. So very critical, if anyone is ever servicing these gauges, the outer side of the glass is smooth. The ridges, or known as prism, must be installed on the inner side of the glass. If someone were to make a mistake and install the glass backwards, doing a maintenance or a rebuild, the glass would tend to look full all the time with the prism on the outside. So that would be a critical error to rebuild a gauge incorrectly. When it comes to the transparent type gauges, there's a few concerns. On the image all the way to the left, this is a gauge laying on its side as if you just set it on a bench. And you can see there's gasketing and glass components and mica shields that are used to guard the glass from the erosive environment of high pressure steam and water, especially as these gauges are blown down periodically by operators. The second image shows the ASME requirement for a 1-inch minimum overlap from one section to the next. So in this application, if I need two window sections to cover the total range or more, anytime there's an overlap, or excuse me, anytime, yes, that two sections or more need to overlap, they must overlap by 1 inch or 25 millimeters as a minimum. If there's a greater overlap, there's no harm in that, but you can appreciate as that meniscus line rises in the level instrument here in the glass, the operator never loses sight of the line all the way through the travel range. Off to the right is showing a narrowed body design of a transparent gauge that would be typically used on process fluids. And you'll see me, or hear me rather, mention this more than once today, that some of these products or similar designs are used in process fluids and stem from process fluids, but unfortunately can make it and migrate into boiler applications. We see this scenario happen sometimes in large chemical plants where there may be hundreds of level instruments, but only a few boilers. In this case, that narrow-bodied gauge has a structural web in order to maintain strength of the gauge for pressure. And even though there's a passage drilled through the center of it, that structural web, if there's 1, 2, or perhaps 3 of them within the visual range of a single window of glass, that can cause an illusion from a distance for an operator to mistake a structural web as a level. And that is prohibited by Section 1 in ASME. So that was brought up in the code about 2008. It's been in the code since 2009 that that specific type of design is prohibited from being used on a Section 1 boiler application. On the ported gauges, you saw in the earlier slide that they display water as green and steam as red. And you may wonder, if you're not familiar with these, how they actually operate. Well, those images on the left of center on this slide show you the plan view or top view looking down onto the gauge glass. As a result, there's red and green colored nowadays LEDs. If you go back 15 plus years ago, LEDs were not in the marketplace on these gauges, and there used to be halogen incandescent lamps used and red and green glass filters. Now on modern lighting systems, these are all LED. So if any of you in the audience today have any of the old time designs, you might want to consider updating those and getting rid of the old unreliable illumination and updating to LED. The LEDs are going to provide 10 to 15 years of normal service life and minimize your maintenance and reduce power consumption. But back to operation, the red light is directed into the back of the glass in such a way when there's no water in the gauge, the red light penetrates directly through. When water level rises in the gauge, the red light is refracted out of position and the green light refracted into place, and you'll see green water. As the level climbs and the level in a particular port changes from red to green, you'll see a horizontal climb, and you will definitely see the change in the port. These gauges must be fitted with the lighting accessories in order to be code compliant. You'll see in an upcoming slide what happens if you do not have a light fixture present and how difficult it must be to find a level. Without those colors and gaps between the ports, you could appreciate how difficult it might be to try to find a meniscus line when you've got 40 to 50% chance that it could be in one of those gaps between the ports. And this question came up about the lighting and being code compliant within the last few years. In section 1, an inquiry was sent in, and this was just reaffirmed that the lighting fixture and ported gauges are in compliance with code requirements for a level gauge glass. Here's just an example. This is on an HRSG plant, and there's a couple of gauge glasses installed, and you could appreciate how tight that walk area is up above, or even just climbing up to that to take a look at those gauges. But with this type of gauge installed in that application, they're easy to read from grade. And also there's an operating chain or parachains for each valve set associated with those gauges, so they can be safely actuated from grade from the operating floor. Now we're going to switch gears and talk about remote or indirect level indicating technologies. And these are the most common technologies that are used in the marketplace today. First is conductivity probes, which are level detection sensors installed in a vertical pipe manifold and specified to be at the locations required by the end user or the boiler manufacturer. And those sensors are fed to a control unit, then in turn to a remote indicator displaying the water level to an operator in the control room. These devices can also supply a 4 to 20 milliamp signal, which is going to be a stepped signal based on the location of the sensors. These devices are typically approved not only as a level indicator, but as a limit control device, which can be used for alarming or tripping. Second, we have the magnetic level indicating devices, and that's a stainless steel chamber. And you'll notice the long leg vertically below the lower side connection there. That's very typical among all manufacturers, because the way these units work, they are designed with an elongated float, and in the upper end of the float, there's a magnet that attracts or repels the attached level indicator. This technology stems from the process level indicating world and has migrated onto boiler applications over the past, I'll say 15 to 20 years. And in 2007, some very strict rules went into effect in the ASME Section 1 of the Boiler Code for these devices. And I'll talk about those limitations here in just a few moments. But you'll notice The indication scale on this application does not encroach into those vessel connections, and that should mimic code requirements for the full range for an operating application on a power boiler. The third type would be a guided wave level transmitter. We'll call this the newest technology that's evolved into the marketplace. And these can work quite well in the application and be designed appropriately for the various pressures of the applications. While there's nothing in the code about mixing technologies, obviously many would agree if I mix technologies, even using the last type, which has been the most common for many, many years now, is differential pressure transmitters. If I have multiple technologies on my vessel, I reduce my risk for common mode error. So I would encourage you in the audience to think about multiple technologies when you're selecting or considering updating any of the equipment you use now for remote level indication. So now when we talk more specifically about some of the requirements in the Pressure Equipment Directive out of Europe, the reference standard is the EN 12952-7. There's a couple areas in there that are of particular importance. One that very much mimics ASME requirements is the requirement for a water gauge glass combined with 2 level indicators. In a few moments, we'll discuss the details on ASME's requirements. This is an important one, these next couple bullets. The connecting tubes between the boiler and a water level indicator must have a minimum inside diameter of 20 millimeters. This next one, I think, is a good statement, important to follow, and I would even like to see this one in ASME. When the water connecting piping is longer than 750 millimeters, so we're talking 30 inches or so or approaching a meter, the inside diameter of the pipe must be at least 40 millimeters, or you might say 1.5 inches. And the benefit in having the larger pipe on the water leg is to further reduce the risk for sediment buildup in the piping or blockage that could result in a false level indication. We'll be discussing an appropriate and proper blowdown method for level instruments here before the end of the presentation. But some instruments, and I put an example sketch here, the one in the lower right-hand corner of the slide, showing a smaller flange, 1 inch size at the top and 1.5 inches at the bottom. 2 different sizes. Of course, the flange faces have to line up perfectly, but this was to meet this requirement that this customer had. Of course, it would be easier to make both pipe sizes the same size. And someone may look at this and say, well, if they're 2 different sizes, I can't install the chamber upside down. Well, that's true. But protecting that water line with reduced risk for blockage, I think, is a very good idea. And EN also requires that the water connecting piping from the boiler be run horizontal to the water level indicator. And sometimes on ASME applications, you may see an upward slope in the water line so that we don't have trappage. But this is a requirement in EN. So I want to try to highlight and contrast some of these things as we go through this presentation today. Some of the other requirements, EN does require an internal self-closing safety device, or commonly known as a ball check. They do not, however, get into the detail that ASME does as far as the requirements of these ball checks. The open position, well, I don't want to go out of order here. The lowest permissible water level on each glass shall be marked. On the water valve gauge cocks, they should be identified if they're opened or closed, or be obvious to the operator by their installation. We'll talk about a couple examples there in a moment. Ball checks are mandatory on the PED applications for gauge glass. They are optional. They're covered in the appendix, subsection A18 in section 1 of the ASME boiler code. Ball checks also known as automatic shutoff valves, and two words for the same thing. And when it comes to the ball check design as required by ASME, the ball in the lower valve must rise and fall vertically within the geometry of the valve. The upper ball in the upper valve can be designed such as this, where it rolls up and down what appears to be a bit of an angled ramp. But this upper valve is not permitted to have a 100% shutoff. ASME defines that you could have a hexagonal seat, a square seat for that ball, or some other method. In our case, we score the seat to prevent a 100% shutoff. And the reason you do not want a 100% shutoff is during startup, during operation. You don't want these valves to shut off completely, preventing a trapped level within the glass that could differ from the real level in the drum. And there are other methods to prevent it by pins on the stem of the valve. But if that upper ball in the upper valve can breathe slightly, then when these valves are fully open, the vertical rising ball in the lower valve can recede or drop down to its resting place, and then the water level is free to travel within the gauge glass or level instrument. So in the unlikely event of a serious leakage or failure, the water will push the ball up to its seat in the lower valve, and of course steam would push that upper valve up the ramp to its seating area. But when I say it's not a 100% shutoff, it really cuts it down to a whisper, or what we'll say, not a dangerous amount of flow when these ball checks do their job meeting these ASME requirements. When it comes to the glasses and remote level indicators, again, ASME requires a glass on every boiler. However, any boiler operated up to 400-pound service or 26 bar, the glass must be kept in service at all times with no option to valve it off. Doesn't matter how many transmitters you have. There's a lot of low pressure boilers around factory workers, personnel, and ASME rules are very clear that the glass will be in service 24/7, highly reliable in low pressure service of this nature. And for anyone to just take a glance at that boiler, you'll see the level, even if you're in a spot where you can't see a remote transmitter if a operator is on patrol for a moment or so. When the operating range exceeds 400 PSI, there's a couple options. The old school was having an operator stationed out at the boiler many, many years ago, looking at 2 gauge glasses perhaps. But the common way today is to have 2 independent, and I'll say at least 2 independent remote level indicators on continuous display, and a gauge glass which may be isolated. However, the gauge glass must be kept in good working order. Now, I want to keep in mind, this is code minimum requirements. Plant rules, insurance carrier rules may choose to leave the glasses in service. The trends that we see where more glasses are valved off and used on an as-need basis is when you start crossing over about 1,500-pound service. In the meantime, if you think about a gauge glass versus your transmitters and the need for 2 transmitters, if I'm that operator sitting in the control room, if I've only got my eyes on 1 transmitter, how do I know it's correct? If I have 2 transmitters, I've got checks and balances, and they should be trending with each other, responding to changes in water level. If suddenly, for some reason, those 2 transmitters start deviating significantly, I have the option on my gauge glass to turn to as a referee to help me determine which indirect remote reading transmitter is reading correctly, so I don't mistakenly pick the wrong one. So keep in mind, these instruments are specified and installed for good reason. You'll notice this in this slide off to the side, depending upon the type of boiler ASME has certain rules that cover the range of the glass is supposed to cover, and a level transmitter, the full range, operating range from low water cutout to at least high alarm. The elevation of the lower end of the glass differs slightly from PED to ASME. ASME has various definitions between fire tube and water tube boilers and diameters of drums on fire tube boilers. But in the case of the water tube, it was a recent change that instead of saying that the low end of the glass be at least 2 inches above the danger point in the drum, now there's a tolerance on section 1 vessels stating the low vision of glass must be 2 to 3 inches above the danger point as determined by the boiler manufacturer. And of course, your low water cutoff and alarms are going to fall within the range of the level instrument. So the whole thought here is once the water drops out of the level instrument, you've still got a bit of a safety bed below the bottom of the glass before there's any risk to the drum internals. In the EN standard, they state that the glass must be at least 30 millimeters below. And that's a different standard than ASME, and that's allowing the glass to encroach closer to that danger point in the bottom of the drum. So there's a bit of a difference there between PED, EN requirements and ASME. You might say the ASME requirement is a bit more conservative, giving you a larger safety bed of water below the bottom of the glass. Here's an example of a control room situation where there are 6 drums. These are 2 sets of HRSGs, and the operator where this photo was taken is looking at 2 technologies. On the screens at the bottom of the image, those are all fed from differential pressure transmitters. On the wall up above, those are conductivity probe devices. Now, if you count those vessels from left to right, the 4th one is empty, but I'd like to point out that what's labeled there as Unit 21 was not in service when this photo was taken. But if you look at all the instruments there, virtually all 6 transmitters, DP type, and all 6 conductivity type are all reading within reason of each other. So that operator's got high confidence in knowing where the water level is in these instruments and their drums. Here's an example of an application, and this is on a low pressure boiler. These are reflex type gauges, but I'd like to point out what this user did was in their application, they're below 400 pound service, below 26 bar. They're only required to have 1 gauge glass. However, they have 2. They know they need 1 in service at all times, but if they have 2, and if 1 ever suffers a leak or a glass erosion, making it difficult to read or staining, they can isolate 1, have the other in service, and not be in violation when it comes to their glasses. When it comes to the remote level indication, they've got a conductivity probe device in the center. Those sensors are underneath that protective housing indicated by that yellow arrow. And they've got 2 differential pressure transmitters indicated by the blue arrow there on the right side of the image. So they've got 3 transmitters, even though they only need 2. If any one of those 3 are out of service for maintenance reasons or discrepancy reason, they're still in compliance with 2 transmitters. I'd also like to highlight, you can see the drain piping coming off of these gauges, coming off of that conductivity probe device. You know, these are in walkways where an operator might walk by. They've got all that low end piping very nicely insulated so that no one suffers a burn risk down near at knee height. And some of the areas on platforms near this equipment can get very tight. So while we're looking at this slide, I mention it again later, but be responsible and take care of your plant personnel. Make sure all this piping is insulated where there might be a risk for personnel or a burn risk. That's a nasty injury to suffer if need be. The last thing, got it coming up on another slide as well, but if you notice that small diameter tubing going off of those differential pressure transmitters. These devices do require periodic maintenance. It's encouraging to those in attendance to check that piping periodically, make sure it can be blown down, flushed, so that you don't have any sediment buildup in those sensing lines. And you're vulnerable in either long horizontal runs or elbow turns, right near a horizontal run, sideways turns. Sediment buildup can cause a false level indication on those devices. Check also on any instrument with the OEM for the instrument itself. They would have the most accurate recommendations and maintenance instructions for any instrument on your boiler. When it comes to magnetic level indicating devices, some of the, I use the word strict ASME requirements. You may not attach a gauge glass to this device. The chamber is made out of stainless steel. It has its own set of isolation valves. It's considered a remote level indicator. It could be equipped with a transmitter, but typically they're installed with an attached indicator. And in the process level world, it's very common to replace glass and use these in the same vicinity, and you see the level where perhaps you read the glass before. However, this does not replace the code required glass. It's an indirect reading device. We're relying on the float within the chamber containing a magnet to attract or repel that externally mounted indicator. For applications where they are permitted, not on a Section 1 boiler, switches are often attached to these devices, and they simply clamp on, screw clamp onto the chamber. It's, you might say, too easy to put those switches in an inappropriate location or down too low. You see that dead leg below that lower side connection again that I'd mentioned previously. If someone installs a switch too low, it could put a boiler at risk. So that's one of the reasons that switches for control purposes are not permitted by ASME. Also, ASME has a design limit for these devices of 900 PSI, or about 60 bar. Part of the reason for that limit is changes in density with the specific gravity of boiler water over a broad range. For example, if one of these devices were designed to be used at 120 bar, and then someone decides to drop down to say 60 bar in operation mode, it could result in a significant level indication error reading falsely high. So a lot of that risk is mitigated by limiting the pressure of these applications. If you are using any of these devices on a water application, be it feed water, condensate tank, or on a boiler application, we would recommend periodic inspection of those floats. Doesn't matter who's the manufacturer. There's typically a flanged access at the lower end of the unit. When that unit's opened up, you can remove the float. If you see the float comes out perfectly clean, then that's a great clean water application. However, if you remove the float and there's a lot of debris of particulate collected on the upper end of the float, it can cause the float to either get lodged, sink because it's become heavier. And in that scenario, you'll learn that in your particular application, that float may need more periodic inspection. So now we'll talk about valving for a few moments. All externally mounted level instruments, whatever type of remote level indicator you're using, any type of gauge glass, they all require isolation and drain valves. And these isolation and drain valves can be many different technologies. You know, the old school was just using gate valves. And because these devices, drains are opened and these things are blown down frequently, over the years, globe valves have become more commonly used, because if the gate valve is not left in a full open position with the frequent cycling of blowdowns that many operators do on these instruments, you can cause the bottom of the gate to wear on a gate valve. And as a result, globe valves have become more common. We'll get more into that in just a moment. The drain leaving a water column, gauge glass, or remote level indicator should be routed to a safe discharge location away from an operator operating those drain valves. We see too many out in the field where it's just a short drain stub right there at the end of the piping. And if it's not routed to a safe place, when those valves are open, you've got a large cloud of steam forming there. And it can be risky for that operator to reach back into that cloud to find that handle to close that valve again. So again, consider your operators, run that drain piping to a safe location. Operating chains on water gauge valves. Some valves are quarter turn, and it's following the manufacturer's instruction. If you look at that ported gauge on the top center, those valves are open with those levers pointing downhill to the left. Those valves are open and linked together, and there's many positions of installing those levers onto the valves and adjusting the chain. So when the handle is pulled on the right-hand side of the lever, both valves will close tightly. There can be a little slack on the chain on the left-hand side, because if one valve is open slightly more than the other, it doesn't matter. But if I have a concern or seepage or a leak when I need a tight shutoff, that's important. And I know those handles are shown very short there, but just to capture it all in one photo, that was just put together with short chains to the handles. Typically, they'll extend down to a lower elevation. When you're using chain wheel valves, you should never install a single chain between the two wheels. In other words, you don't want to do a bicycle chain type arrangement. All the level instrument manufacturers typically make these valves with rising stem and threaded components, and trying to manufacture two valves that are going to be identical with the teeth on the chain wheels in exactly the same place when two valves are closed is quite difficult. So if someone installs a single loop of chain between the two valves, what's likely to happen is the first valve to close stops the chain. Hence, what you see here is separate chains for each valve. And when you look closely, the gauge manufacturers will design these typically so that the chain wheel on the upper valve, steam valve, extends further away from the valve chamber than the lower valve, so that these chains will drop down next to each other without tangling each other. If you look at the image down below, the ASME code requires these valves to have some indication of their position as open or closed. I mentioned the one up above with levers, and operators quickly train to see by the position of a lever what's open or closed. On a chain wheel valve, in our case, we've devised a tag and instruct our customers how to install that tag, so when it's in the appropriate place on the chain, they can see that valves are open or closed. And you can see here that that operator's head is much below that upper valve, so definitely there is a need for a chain there. ASME requires anytime a top or bottom valve is more than 2 meters or approximately 7 feet above the operating floor platform, some method of operation is required. They don't use the word chain, but chain is the most common method. There would be no reason someone couldn't use electric or pneumatic actuators. You could use reach rods, different methods. Chain seems to be the most common way, but if they use the word chain in the code, it would sound limiting. So they use the word mechanism in the code rather than chain. I mentioned earlier about the demand for globe type valves, and they work very well for isolation on a gauge glass or level instrument. But I'd like to point out that not all globe valves are appropriate. If you look at this illustration to the left of a traditional globe valve, the inlet would come in from the left, outlet to the right, and you can see there's more or less a path for a sediment trap on that inlet connection below the tip of the stem. That would not be permissible for use on a Section 1 ASME boiler design. If you're using a globe valve, what's shown off to the right is the geometry of a Y pattern globe valve that when it's installed and the valve is open, if 1/4 of the inlet port diameter is above the seat when the valve is open, that makes that a routable valve. A wire could run straight through that valve. This type of valve design is more resistant to blockage and sediment, and by a lower risk, the reliability is much better, and this is what would comply with PG requirements in Section 1.
Excuse me, Jim, you've got about 5 minutes so that we can have some questions, please.
Very good. I'll move it along. Thank you. Isolate some of the things we're going to talk about in code violations, and as we near the end of the presentation, is we'll show isolated inoperable water gauges as a common thing, lack of proper maintenance procedures, missing water gauge glasses, maybe someone removed them and put process type instrumentation on there mistakenly, missing illumination from water gauges, and inadequate display of remote level indicators in the control room combined with isolated gauges. And what we mean by inadequate display would be a level indicator represented on a screen, as we saw in an earlier image from the DP transmitters. But if that screen is manipulated for other purposes, the operator could lose sight while they're using it for a different reason than level indication. That could cause a violation. Those two level indicating instruments must be on continuous display. So here's an installation error as an example. This contractor made a huge mistake by locating this column and gauge glass around this outlet pipe and sloped it down inappropriately. And you can see they've in essence got a water trap level indication situation going on here. When it was remedied, it was repositioned back to the original design that was documented. This was absolutely just installer error. Fortunately, it was caught before the unit was put into service. And you can see everything's brand new here. Here's a case of a ported gauge with no lighting accessories on it. Very difficult at best to read a level. Not to mention it's a hot device in what could be a walkway here. When the gauge was replaced, properly fitted with the lighting information or instrumentation attached to it, you can see 4 greens, 3 reds, and easy to read from a distance. I know where my level is and I'm satisfied as an operator. Here's a case I just mentioned a few slides back, that every gauge glass must be fitted with a drain connection and routed to safe discharge. Unfortunately, the drain on this application was welded shut. There's no way to relieve the pressure out of that gauge if I was going to conduct maintenance on it. This application off to the right shows a magnetic level gauge with indication scale below the water leg coming off this drum, and this was on a high pressure drum on a heat recovery steam generator. If the level's really down to that connection but not below it, even if it were below, this trapped area here would always show level, which is a bad situation for an operator. Here's a case where a magnetic level gauge was ordered incorrectly by a customer with an inappropriate scale. And you will see this if you look at magnetic level gauges just by an assortment of manufacturers. It's not uncommon for scales to encroach into the design connections, but you have to keep in mind, if it's a fluid like a static tank, not even under pressure, it may cause no harm, no foul. However, if we're on a boiler water or a supporting vessel, you can appreciate what could go wrong. And here we have a technician replacing the scale to make this installation code correct. I mentioned earlier, check all your piping, check these sensing lines, any of these places that could cause or result with sediment that would affect the level indicated. Some recommended maintenance tips. Inspect your gauges and valves routinely for wear or leakage. Plan annual maintenance intervals on these devices. Maintain insulation on the mating piping for operation and personnel safety. I cited that low piping on that, or insulation on that drain piping earlier. Apply heat tracing to any instrument indicating application that may be subject to freezing conditions. There's a lot of applications installed outdoors where this would be a huge benefit. Remedy any concerns before they get worse. Leaks only get worse. Steam damage, steam cuts can happen in valves. The longer it takes to remedy a problem, the more costly the repair can be. Use OEM parts, OEM resources for the most accurate information for your instrument and also to maximize the service life. Proper blowdowns should not exceed 20 seconds. And here's an illustration that we contributed, and this is actually in section 7. And this talks about how to properly blow down instruments. And many operators simply just open the drain valves, but when you do that, steam and water are both fighting to go out the drain. And if you do not have the ability to isolate the steam and flush the water leg by itself, just by opening the drain, you're not doing anything to necessarily assure yourself that that water leg is free flowing and free from debris. We have a blow down animation that runs about 6 minutes. You can see it on our website. It's our animation and item on our website that has more views than anything Clark-Reliance has. And we're proud of that. And we've helped educate a lot of folks with that animation. If it applies to you, I encourage you to go to our website and see it. We're just about near the end here, just a couple slides. So summary recommendations: consider LED lighting if you're not using it already on your gauge glasses. Consider specifying multiple technologies for your remote level indication applications. Maximize your reliability, minimize your risk against common mode failure. Consider proper maintenance procedures. Consider logging your maintenance on these devices, how often you're servicing them. We're happy to help in any way we can. If you'd like to send us photos of any of your applications, we'd be happy to take a look at them and give you some comments or suggestions. On your piping, always do that insulation. It takes care of personnel safety. It helps increase level accuracy against temperature loss, also reduces condensate formation and high temperature steam service applications, which could help extend service life of the instrument and improve level accuracy. Piping, we like to see it less than 6 feet or 2 meters from the drum to the level instrument. Keep in mind all these other vital applications that are not necessarily a boiler drum. Could be deaerators, condensate tanks, blowdown tanks, feed water heaters. Any of these applications all require important level instruments. Don't neglect these devices. They should be cleaned, inspected. If your plant has been down for COVID, many plants were shut down, closed, and being restarted. If plants were idle, you might want to take a little extra time to check all these instruments, making sure that your piping is clean, free flowing. When you blow something down, close the valve and that it responds promptly to the water level. Clark-Reliance has a YouTube channel loaded with a lot of manufacturing videos that we've created for boiler code compliance, 2-minute tips for proper care of equipment, a lot of helpful information, and you can look at those on your own at any point in time. My final slide here is I want to thank you all for the attention. We'll have a few minutes here for questions, but we have these inspection booklets. These are available at no cost, and feel free to contact us or go to our website. And I don't know if Barry's going to mention, but my email is jkolbus, that's K-O-L-B like boy, U-S, at clark-reliance.com, or you can reach one of our application engineers for assistance at any time. Barry?
Yeah, Jim, thank you for a nice presentation. Clark already put your email on the chat site, so everybody should have that. there's a couple of questions mixed between what came in as registration and then a couple that were in the chat. So let's do the one from the chat first. And again, I'll just read them out. If there's any clarification, we'll get the person to come online. The first one's from Nicholas Patel. Does the same ASME boiler code allow you to run with 3 GWR and no DP for level control?
Yes, that would be permissible. There's nothing in the code that would prohibit someone from using all of the same technology for remote level indication, just that you have 2 of them. And my comment or suggestion was, if you have multiple technologies, they can't fail in the same manner. So you eliminate a risk for common mode failure, but that is permissible.
Okay, good.
Go ahead with your next question, but I had one comment I want to throw in before we're done.
So there's you want to continue on that same question?
Well, all I'd like, it's not related to that question, but what I did want to mention is if anyone has any concern about the level instruments that they're using, we would encourage you to contact your local jurisdiction inspector, your local insurance carrier, or us. We're happy to share our opinion, but going to your local folks, their requirements, they could go beyond code minimum for your particular plant, and they're a good resource to consult.
Good. Yeah, thank you. Jim, there's one from Sean Bowler in Trinidad, and he asks about the frequency of doing calibration or function testing of drum level transmitters.
All right, depending upon the type of device that it is, if it's a conductivity probe device, there's nothing to calibrate because those sensors are on fixed locations. Same with a gauge glass, it's installed per the manufacturer's instructions or the boiler manufacturer's requirements. When it comes to another level indicating transmitter device, I would recommend that you consult with that manufacturer to find out what they recommend, what they have documented for you, so you follow their specific procedures and frequency.
Okay, thank you. There's a question here, and it didn't have a name by it. Has anybody experienced a precipitous drop of about 5 inches and then recovered in drum level with steady or increasing feed water flow?
That's an unusual one. I saw that come in. We discussed that one earlier. What could be going on? I would be concerned about piping and making sure that there's no restriction in any isolation valves or in the piping itself between the isolation valve and the drum. If there's a restriction there, that could cause a delay in response. Even under loads, that water should be getting replenished and they should not be suffering that type of restriction or loss. So that would be the first thing I would take a look at, see if any discovery is made of any blockage. And also, if they've got more than one instrument on the drum, is this phenomenon occurring in more than one instrument or just one by itself? So a little bit of research on the piping is where I would start.
Yeah. So Jim, you covered some of this, but I'll just ask because the person put it in. Silvio Grigio from Petrobras in Brazil asked about what about magnetic level gauges instead of level sight glasses? I know you covered this, but I wondered if there's anything else you wanted to just indicate here.
Well, again, it would apply to which code of construction you're following. If they're following ASME construction, you've got that limitation of 900 PSI. That limitation is not in the EN requirements. So first of all, which rule of construction is being applied in that plant on that boiler? That would be my driving concern. And then all those other issues I mentioned about magnetic level gauges on boiler water application, making sure you got a clean float, making sure you got a float appropriate for the operating conditions. And if those operating conditions are going to vary widely, and what I mean by operating conditions is operating pressure, you might want to take a very close look at that to make sure you're going to get an accurate read on the level. Once again, if the operating level changes significantly lower than it was intended to operate at, the float will typically ride high, causing a false high indication relative to what's in the drum. Good question, though.
Good. Thank you. So I have one here. I noticed, Jim, that you didn't say anything about the chemistry, the cycle chemistry on these units. And, so is there anything general that people could look at, or is there anything that people need to know between the difference between operating with reducing treatments, which would produce magnetic particles that I think are the ones that you were referring to as sediments and debris,
Yes.
and oxidizing environments, and then particularly with reference to the magnetic systems, because you do have magnetic particles in the system.
That is correct. And that's why some of the need for blowdown on this equipment, as we mentioned, and we have that video available to show people how to do that appropriately. Also, to maintain water quality, there'll be continuous blowdown systems, often on many drums. The water chemistry is getting a bit out of our area of expertise. However, the American Boiler Manufacturers Association does have a document about water quality. So that's one resource for our attendees today. If they were to go to abma.com or American Boiler Manufacturers Association, you can get some information there. Also, another good reason to go back to the original boiler manufacturer to determine what water chemistry requirements they recommend for the boiler that they've provided you.
Yes. And of course, you also have IAPS, which is over your left shoulder on the background, and that can provide that information. There's one other just come in. We'll probably have to make this the last one, Jim. What is the highest recommended indicator that can help minimize drum shrink and swell events? This is from G. Martin.
The highest level indicator. I'm not sure that I clearly understand this question. We're going to give it a run, but if this is not what they're looking for, maybe they can write me or contact you and we'll follow up after. First of all, the code requires that a level instrument cover the full operating range. So that's going to go from the low water cutout up to at least what would be high alarm. So the boiler manufacturer is going to make that determination. They're going to determine that range, how that device should be attached on the piping, and that would be your starting point. I'm not sure what he's getting at by shrinkage and changes in level. If he's talking about density error, that we can address in a more detailed conversation if they wish, and I would encourage them to contact me directly.
Yeah, okay. So Scott, if maybe this person would like to verbalize it, if we have a minute.
Sure, he's on. Can you hear me okay?
Yes, we can hear you.
Okay. It was more related to, since I deal in projects where during the startups or shutdowns, you get the surge or swell event inside of the drum, which affects the whole startup procedure and how fast it can get going. So I was wondering if there's some kind of measuring device or indicator is the word I'd use. Maybe it's not the correct one. To then something that can help, I don't know, with the whole control algorithm with the whole plant or the startup to help minimize those events. I know there's a lot of things that go into minimizing surge and swell, but I was wondering if there's something specifically related to this hardware that can help minimize, so you can start up faster, basically.
I don't have a specific requirement for you when it comes to level instruments. I wish I had a better answer for you. I think we'll do a little research on that. And I'm going to ask Barry to send me your contact if you don't mind, and I'll do a little follow-up with you independently.
Yeah, that's fine. That's fine.
Yeah,
thank you.
Yeah, thank you for the question. And Scott, I think will be able to send it to you, Jim, or you can or you can send it to either of us or Bob, and we'll get it to Jim. So, Bob, I think that's just about on time. We went a couple of minutes over here. And I don't see any other questions. So Jim, thanks very much.
Barry,
And,
we did get a response to help out on that last question. Nicholas Patel says that GWR helped his startup swell, faster response than DP, and a better reading and less false swells.
Okay.
Barry,
Okay.
you are a couple of minutes long in the UK, but here in the US, you're only 1 minute overdue. So
Okay.
you did
Well,
well.
we're closer to Greenwich Mean Time, of
Yeah,
course. Yeah.
I realize that's the difference. Okay, enough of that.
all right, well, thank you all for allowing me to present today. I appreciate the opportunity and I hope it was educational for the attendees.
Yeah, Jim,
Thank you.
is your presentation available? The slides, if people ask for it.
Yes, it is. And you've
Okay,
already got it.
so if you want Jim's slides or Eugene's, you can request them of Scott, or you can request them directly from Jim, me, or Barry.